Here we are at example 7 from our 8.3 number 2 set of notes. We're asked to graph this following rational function. And typically how we start out with these is we're going to go ahead and see what is our horizontal asymptote. So for our HA, we're going to go ahead and look at him first. We notice that the degree is larger on the top than it is the bottom. And as a result of that, we will actually not have an HA here. So none. Next, typically what we do, simply because we don't know whether we have holes or vertical asymptotes or things like that, is we go ahead and factor this rational function. And when we do that, if we look carefully on the top, we can pull out an x from all these terms. And we would be left then with x squared minus x plus 6. On the bottom, we would have x plus 3 times x minus 3, because we are looking at the difference of two perfect squares there. It looks like on top we can actually we cannot break that down any further. I thought this was a minus here. And as a result, we unfortunately just can't break down the top anymore at all. It looks like nothing really cancels out here, so we shouldn't run into any holes. But what we can do next is just follow kind of that same normal procedure of setting the bottom not equal to 0 to see maybe where are the vertical asymptotes. Yeah, we're not going to have any holes, but we could have some vertical asymptotes. So for the VAs, we're going to set this x plus 3 equal to 0, and the x minus 3 is equal to 0. And we pretty much just go ahead and solve for x from here. So we would have x is equal to negative 3, and x is equal to positive 3. So just graphing those, we have negative 3. And you could save this for the end too, but it doesn't really matter too much with the graph. So negative 3 is one of our vertical asymptotes, positive 3 is the other. Next, what we go ahead and do is mention typically the holes. Unfortunately, we just don't have any of those here. So for our holes, we don't have any. After that, we would then move typically onto the slant asymptote, if there is one. Here we notice that the degree is exactly one more on top than it is the bottom. So we will have a slant asymptote. And unfortunately, because we have a degree of 2 on the bottom, we can't use synthetic division to find that. We are forced to use the long division. So let's go ahead then and set that up. We have x cubed. So this is for our slant asymptote. X cubed minus x squared plus 6x is being divided by our x squared minus 9. First of all, what we're going to do is ask ourselves what times x squared gets us that matching x cubed that we're hoping for. We're trying to get this x cubed where these two match. Well, the only thing that can do that is x. So x times x squared gets us that x cubed that we want. This negative 9 is along for the ride, and as a result, what we're going to do is multiply that x times negative 9 and end up with negative 9x. Now we're going to go ahead and throw him under the other x term because we are trying to combine our like terms here. We have negative 9x right underneath that 6x. So again, it kind of just goes back to the placements of items. We didn't have any x squared terms, so you know, you kind of just you could have like plus 0x squared here if you really want. It's not going to change anything. By properties of long division, thinking back to grade school, we always swap those signs of everything. And we can see really quickly that this x cubed cancels out with this x cubed. You have negative x squared minus 0x squared, well, you still have negative x squared. You're not subtracting any x squared, so that's why you're still just having negative x squared. We had positive 6x. We're now adding 9x, so that gives us a total of 15 x's. We pretty much just now repeat the exact same set of steps. So what times x squared gets us negative x squared? Again, we're trying to match this up. And there's only one item that can do that. Negative 1. Negative 1 times x squared gets us that negative x squared. Again, negative 9 is along for the ride. Times negative 1. End up then with positive 9. 5 properties of long division. We're going to go ahead and swap those signs just like we did a moment ago. And when we do that, we do notice the x squareds cancel out, leaving us 15x minus 9. Now, because you can't multiply something by x squared to get 15x, you actually can, but we're not going to dive too much more into that. I mean, we've already kind of seen that. This would be our remainder, or you could write this as plus 15x minus 9 over x squared minus 9. You can do that. But ultimately, again, this stuff is pretty much irrelevant. It plays a very, very little role in the grand scheme of things, and that's exactly why we pretty much just ignore him altogether, that remainder. And again, we've talked about why that is from class. But our slant asymptote comes out to be y equals this x minus 1. So there is negative 1 for the y-intercept, and we do have a slope of 1. So from that point, we're going to go up 1 over 1, 1 over 1. Same thing in the other direction. So more or less, we should see some asymptotes doing something like that. Next, what we're going to go ahead and do is try to find the x-intercepts from our simplified version of this thing. Well, here is our simplified version, and as you can see, nothing really canceled out. So as a result, what we can go ahead then and do is, just like we normally find x-intercepts, we're going to set f of x or y equal to 0. So f of x is going to be equal to 0. Yeah, this is for our x-intercepts. And the reason why we're doing that is because we are trying to cross this x-axis. The y values for f of x is always 0 there. Never changes, it's always 0. So we have x times x squared minus x plus 6. X times x squared minus x plus 6 over x plus 3 times x minus 3. And at this point, we really just want to go ahead and try and solve for x here. Doing that, we would multiply both sides by the bottom, x plus 3 times x minus 3. But pretty much when you do it on the right side, all this stuff would drop out, leaving you with just your numerator. So that x times x squared minus x plus 6 is equal to, on the left side, 0 times this piece right here, this x plus 3 times x minus 3 is still 0. And as a result, you're pretty much just left with that numerator, again using that shortcut rule that we've seen. Now going ahead and using the zero product property, we know that we can go ahead and break each of these up and set them each equal to 0. So this x is going to be equal to 0, and this x squared minus x plus 6 is also equal to 0. Again, just looking at this one right here, It can't be factored, unfortunately, and usually when it cannot be factored, when it's in this kind of form, this trinomial form, you kind of have to resort to the quadratic formula, and would not be surprised if there are some imaginaries happening here. So looks like we have x is equal to the opposite of b. So in this case, the opposite of b here is negative 1 plus or minus the square root of b squared, so negative 1 squared, minus 4 times our a value, looks like it is 1, times our c value, positive 6. And this is all over 2 times our a value, 1. After this, it's just kind of simplifying things up. So we have x is equal to positive 1 plus or minus the square root of negative 1 squared, comes out to be positive 1. Negative 4 times 1 times 6, looks like that comes out to be negative 24, all over 2. So then x is equal to 1 plus or minus the square root of negative 23 over 2, which pretty much just simplifies down to be x is equal to 1 plus or minus I, if you pull that negative out, square root of 23 over 2. And unfortunately, we do see that this is a complex number with that imaginary component, and that's really, really difficult to graph on the real number plane. And as a result, we pretty much just can't graph this on our typical XY coordinate graph. So really kind of the only x-intercept that actually exists in the real plane comes out to be 0. So again, this is roughly what this graph would look like. I'm just kind of curious, if I was to plug in some values, well, it should do something like this in the middle. And I'm not certain if it's going to go up like this or if it's going to be down. If I had to guess, it's probably going to go down and up. But what we could do is just test a few points. If we tried, like, for example, negative 6, we could throw negative 6 into this function and see what we get. If we throw in positive 6, we could then again see. But again, it pretty much just boils down to testing values and testing different x's and seeing what your y's come out to be. But for the sake of time, we'll just go ahead and do Desmos. And here is our final image for the graph. We do notice that it kind of did go underneath and above at those ends, and it looks like it also actually crossed that slant asymptote. Now, finding out what that x value is simply just setting the slant asymptote and your you could do your function, which, I mean, you could do the original function if you really wanted, or the factored one. It doesn't really matter. So let's go ahead and do that right now. So we'll just go ahead and use the original function. Again, this is for our slant asymptote crossing. We have our slant asymptote as y equals x minus 1. So again, this was our SA. Y equals x minus 1. And our original function, let's say he's green, so the original function was x cubed minus x squared plus 6x all over x squared minus 9. And pretty much just using the substitution method, we are taking this guy from the slant asymptote and throwing it into for y in the second equation. Let's see, for what x value is that actually happening at? We have x minus 1 is equal to x cubed minus x squared plus 6x all over x squared minus 9. Multiplying both sides by that x squared minus 9. Here where they end up dropping out. On the left side, we see that we would have to go ahead and FOIL that, giving us then x cubed minus x squared minus 9x plus 9 is equal to x cubed minus x squared plus 6x. If we subtract x cubed from both sides, they're gone. If we add x squared from both sides, those are gone. We'll go ahead and add 9x to both sides. That way 9 just by himself. We then end up with 9 is equal to 15x. So it looks like this cross is happening at 9/15, or x is equal to 3/5. We would then have to go ahead and throw that in to find our y value, but the main idea here is that it is crossing that slant asymptote. Kind of curious where that's happening at. So we've got, again, our function. It is crossing, actually what we can do is just do this, actually x minus 1, 14 minus 1. There we go. We can see it hugging now, that asymptote. And it is crossing at 3/5, just like we were projecting. 0.6 and negative 0.4. So there's that cross. And again, you would just take this x value, if you throw it into the original function, you could throw it into this one, doesn't matter. But again, the final image should look something a little like this. Again, though, that is our example 7 from our 8.3 number 2 set of notes.